Now we're going to talk about addition and carries, which we've seen a little bit of before, and go into some detail about multiplication. So addition and multiplication. Binary addition is pretty straightforward. Here's the truth table for adding up numbers, 0 plus 0 is 0, all the way up to 1 plus 1, which in binary is going to be 1, 0, or 2. Remember how this works. If we're adding up two numbers, we first look at the numbers on the right, just like we would with normal addition in decimal. We add them together, and if we generate a carry, we then bring that carry over to the next column, add up that column, and get our final result. So let's take a look at an example. Here I'm going to add 186 in binary plus 55 in binary. And the result is going to be 241. And we can look and see at those carries. Here are the carries for the decimal add and the carries for the binary add. Binary multiplication is similar to decimal multiplication as well. Here's the sort of truth table for binary multiplication. If I have a 0 anywhere in my multiplier, I get 0 out because 0 times anything is 0. And if I have a 1 in it, 1 times 1 is 1. So multiplication tables for binary are really simple. Let's take a look at an example. So here's the multiplicand, and here's my multiplier, and now I'm going to multiply it together. And I've colored the digits here by each step in the multiplication process. So first we're going to do the rightmost digit. We multiply that out. Well, 1 times 0 is 0, 1 times 0 is 0, 1 times 1 is 1. Because that digit is a 1, we basically copy the multiplicand down. Now we move over one position, and we do the same thing. Because the red digit is also a 1, we copy it down. But when we get to the orange one, the orange digit in the multiplier is a 0. So here we don't copy it down, we just put down zeros. And similar for the green, because it's a 1, we multiply the multiplicand by 1s, and we get the same thing to copy down. Then when we've got all these partial products, we just add them up to get our final result. So you'll notice that the multiply approach here is exactly what you do out by hand. It's to sort of shift over by one place and multiply by the digit in the multiplier. In the case of binary multiplication, multiplication is simpler because you're always either multiplying by 1, in which case you get the same thing as you had before, or 0, in which case you get all zeros, as you do with the orange value here. Now there are different ways to design multipliers, and I'm going to talk about two general types, parallel and serial. So in parallel multiplication, we have our multiplicand and our multiplier, and we have this array of partial products, just like we saw in the last example. But what we're going to do in the parallel multiplier is we're going to add them all up together at the same time. So every one of those little dots there in the partial product array is going to be an adder. In serial multiplication, we have only one adder, and we're going to have a lot of control logic. And so what we do here is we do the shifts and adds one after another. So we have one adder that we're going to use over and over again for each of the shifts and adds. So when we look at this n by n multiplication, we have two inputs that are each n bits, we can see that we get 2n output bits. That is, we get twice as many outputs. So here's a question. How does this work with the 32-bit registers and MIPS? So if we multiply two 32-bit numbers together, we're going to get a 64-bit result. But we don't have any 64-bit registers in our MIPS architecture. Well, the answer to how we deal with that is we have special high and low registers for the two 32-bit halves. So that when we do a multiply, the top part of the 2n bits is stored in the high register, and the bottom part is stored in the low register. So what we see here between parallel multiplication and serial multiplication is that you can do a trade-off. You can either use lots and lots of adders, which is going to take up a lot of space on your chip, and do a parallel multiplication, or you can use a single adder, which will take up less space, but now you have to do multiple operations. You have to do each shift and each add separately in the serial multiplier. So let's walk through how serial multiplication works. Here's our serial multiplier. We're going to have a multiplicand and a multiplier. We're going to multiply these two together, and what we're going to do is we're going to generate a bunch of partial products. So the first one is going to be 0, 0, 1, 0, because we took the blue digit in the multiplier and multiplied it by the multiplicand. Then we'll have 0, because we take the red digit, which is 0, and 0 times anything is 0, so forth through the rest of our number, and then we're going to add them up. So what we're going to do in the serial multiplication is we're going to do each multiply and add in one step. So we'll do multiple steps to get there. So here's our architecture. We have a multiplicand and our multiplier, and down at the bottom we have our product. Now what we're going to do is we're going to shift the multiplicand over and shift the multiplier over to the other side. As we do this, we're going to look at the least significant bit of the multiplier and decide if it's a 1 or 0. If it's a 1, then we need to add it in, and if it's a 0, we don't. So based on that bit, we're going to decide whether we do an add. So let's walk through this. The first thing we're going to do is check the least significant bit and add if it's a 1. It's because we're looking at the blue part over here, looking at this first digit, and we're going to walk through it. So we check the most significant bit. It is a 1, so now we're going to go ahead and do an add. We add in the multiplicand, so now we're taking this part down here, and we've decided that we're going to add it in because there's a 1 up there. We go ahead and add it in, and now our partial product has that added in. Now we're going to go and shift to move on to the next bit. So now we're going to look at the red digit here, and to look at the red digit here, we don't want to look at the least significant bit 1, so we're going to shift over. So we use our shift, we move our multiplier over, we use a shift to move our multiplicand over, because now we have to line it up moved over one spot. Now we go on and we're going to look and see how to calculate this next partial product. So we look at the least significant bit, now it's a 0, because we shifted the multiplier over. Since it's a 0, we don't do any adding, because we don't need to add in 0, so our product doesn't change. Now we move over to the next bit, and to move over to the next bit, we're going to shift our multiplier over. So we shift our multiplier over, and we're shifting our multiplicand over because now we need to line up moving one step further over here. We go ahead and check the least significant bit so that we know if this should be all zeros or if we should multiply by 1. The least significant bit is 1, so we go ahead and we add in that value, and now we've got our next partial product added in. Finally, we shift to move over to the last digit. So we shift it over and we shift our multiplicand over. Now we go in to generate the partial product. We checked if we should multiply by 0 or 1. We're multiplying by 0, so we don't need to do an add, so we don't need to add in anything more, and we get our final result. So for the serial multiplication, what we're doing is we're doing each partial product one after another and adding them up. And we do the adding only if we're multiplying by a 1. If we're multiplying 0 in the multiplier, then we don't need to add anything because 0 times something is 0. So here we have each of our shifting and adding steps done one at a time. The benefit of this is we only need one adder, because we're only doing one at a time, but we need many steps. If we're multiplying a 32-bit by 32-bit, we're going to have to go through 32 different steps, that's 32 cycles, to get that multiplication done. You can imagine how much that will slow down a processor. Parallel multipliers don't do that. They take this partial product array and they do it all together. So first they generate this partial product at the same time as this one and this one and this one, and then they have a whole bunch of adders which add up all these bits to create the final result. So a lot of logic gates, a lot of circuits to do it all at once. Have to build a whole bunch of adders to do this, and it's faster, but it's much larger. So let's take a look at some examples of modern multipliers. Here's a multiplier from 1992, ran at 100 megahertz and was made in 800 millimeter technology. So you can see here, here's the actual actual multiplier, here's the circuit, and this is basically what we had before. What they did was they took this part here and they folded it over. So there's sort of an upper and lower triangle here, and they shoved them together by folding it in half. Now let's look at how this changed over time. Here's an array from 1996, it's a multiplier. It's made in a 500 nanometer technology, and it runs almost twice as fast, and it's a little smaller. Here's one from 2002. So this is 10 years later. It's now running at 1000 megahertz and made in a much smaller technology. And finally one from 2006 made in 90 nanometer technology. Now if you look at this, we can take that array from 2006 and we can see how small it is compared to the array from 1992. This is why these sorts of multipliers are becoming more and more common, because as we get to put more and more transistors on, it's very easy to build a fast multiplier that does the whole thing in parallel. A long time ago, when we had many fewer transistors per chip, you wanted to use serial multipliers because you couldn't afford to put that many transistors just doing multiplies. So they used to be a real problem to build, and these days the question is how fast we can make them, not how big they are. So let's take a look at some of these design trade-offs. Here's a comparison of absolute speed and area across these four designs. And what you see is that by the time we get up to 2006, we're much faster and enormously smaller. The absolute area has gone down by over a factor of 5. Now, the absolute speed hasn't gone up as much because they're pipelined. They run at a higher clock speed, but each multiply takes multiple cycles. What's more interesting is to look at how they're normalized. So if you'd taken each of these multipliers and built them in the same 1992 technology, what would they look like? So in terms of area, what you see is it about doubles. Between 1992 and 2006, we're using twice as many transistors to make a multiplier. If you look at the speed, just due to the changes in how they're designed, they run almost 3 times as fast. So we use twice as many transistors and we get about 3 times the speed up. Now look at the effort. So the effort is how complex a design we're using. You can see that from 1992 up through 2002, the designs got more and more complex, but then something happened. In 2006, the design complexity went way down. That was people decided it was more important to make a simple multiplier than it was to make one that was more efficient in area or faster in speed. And in fact, the area went up a little bit when they made it easier to build. So what you see here is that the trade-offs change as the technology changes. Today, the area is free. We can put down as many transistors as we want, but the speed and the effort of designing are expensive. So now people are optimizing for building circuits that are easier to build rather than building ones that are small or necessarily fast. So let's do a quick summary of addition and multiplication. Calculations are basically the same as in base 10. We saw the carries and we saw how you do multiplication. Addition can be built very quickly in circuits, and multiplication can be done that way too, but you need a lot more circuits to do it. Subtraction with unsigned numbers is messy. Division is always messy. You can take a look in the book for those details. And the next thing we want to look at are signed numbers. So far we've just been talking about unsigned numbers, and now we'll do that.